Hello, today we're going to talk about oxidation and reduction reactions. Sometimes we call them redox reactions. So redox reactions always involve a change in the electrons. There's always a transfer of electrons. Remember the acronym oil rig. Oxidation is losing electrons, reduction is gaining electrons. So if you have something losing an electron, the electron has to go somewhere. So it goes to the other substance that becomes reduced. So they always happen together. Redox reactions must have an oxidized thing and a reduced thing. Okay. Sometimes we'll split those up into half reactions. So we'll say there's an oxidation half reaction and a reduction half reaction. It's just a way that chemists can look at just the loss of electrons, or they can look at just the gain of electrons, but they would never happen in isolation in real life. They have to be paired together to make an overall chemical reaction. And then, of course, the easiest way to track whether or not something is a redox reaction is through oxidation numbers. Now, just a brief review of oxidation numbers. I'll do a couple examples just to kind of review them. Let's try H2SO4. It's a strong acid. But the oxidation numbers of all three of those elements must add up to 0 because the charge on the compound is 0. So something from the hydrogen plus something from the sulfur plus something from the oxygen, they have to add up to 0. Oxygen in compounds is always -2 for its oxidation state, unless it's hydrogen peroxide. So oxygen overall, because there's 4 of them, has a -8. Hydrogen is always +1 in a compound, unless it's in a metal hydride. And because there's 2 hydrogens in that compound, it winds up having a +2 charge. So in order to get this to add up to 0, the sulfur therefore must be +6. Oxidation state. And remember, we always write the sign first and then the number for oxidation number. Now, if I have something like Br2, its oxidation number is 0 because it's an element in its standard state. Bromine is diatomic, so it's in its standard state, it will be 0. Now, if I have something like Al3+, that's a monatomic ion, one atom ion. So its oxidation state is the same as the charge. And then if you have an ion like, let's do MnO4-, permanganate ion. Whenever you have an ion, the elements have to add up to the charge on that ion. So in this case, they have to add up to -1. Oxygen is -2 in a compound, so that's -8 overall. In order to get this to add up to -1, the manganese must be +7. And so that's how you would do oxidation numbers. Now, remember, if something is increasing its oxidation number, that means that that substance was oxidized, and if something is decreasing its oxidation number, that substance was reduced. And that's over the course of the reaction. And also remember, if nothing changes oxidation number from the reactant side to the product side, then it is not an oxidation-reduction reaction. Okay, so there's a few steps that we're going to use to balance redox reactions. The first thing you want to do is write the half reactions. So you'll write an oxidation half reaction and a reduction half reaction. Second thing, you will balance all of the atoms except for hydrogen and oxygen. We're going to leave those. So any other atom, you're going to balance by using coefficients just like you normally would, and balance both half reactions in that way. Third step, you will balance the oxygens by adding water. Fourth step, you will balance the hydrogen atoms by adding hydrogen ions. Fifth step, you will balance the charge by adding electrons. Then you will make the electrons match. In both half reactions, they have to have the same number of electrons. Like if one half reaction loses 5 electrons, the other half reaction must gain 5 electrons. You can't just make them appear or disappear. And then finally, you will add the two half reactions together. Okay, so here's an example. We're going to split this up into two half reactions. So the manganese, or the permanganate ion, forming the Mn2 plus ions is 1/2 of that reaction. The Fe2 plus ions forming Fe3 plus ions is the other half of that reaction. Once I have my half reactions, I need to balance any atom that is not hydrogen or oxygen. So on the left side here, I have one manganese, that's good. On the right side, I have one iron, that's also good. The next thing I'm going to do is balance oxygen atoms by adding water. So I have 4 oxygen atoms here. I need to add water molecules to the other side of the reaction, and I need to add 4 of them to get 4 oxygen atoms on both sides. And on my other half reaction, I don't have any oxygens, so I don't need to add water. On the left side, next step is to add hydrogen ions to balance the hydrogen atoms. So I have 8 hydrogen atoms on this side, so I need to add 8 hydrogen ions on the reactant side. And there's no hydrogens on the other half reaction, so I don't need to balance any hydrogens there. My next step is to add electrons in order to balance the charge. So I'm going to start with the iron one, I think. Iron has a 2 plus on this side and a 3 plus on this side. In order to get them to be the same charge on the reactant side and the product side, I need to add electrons. Specifically, I need to add 1 electron, and I'm going to add it to the product side because electrons are negative, so this now adds up to +2, which matches the +2 on the reactant side. So that's your clue, then, that this is the oxidation half reaction because it's losing electrons over the course of the reaction. We could have figured that out using the oxidation states. 2 goes up to 3. Let's go ahead and balance the charge on the other half reaction now. I have 8 positive charges and 1 negative charge. So that means my overall charge on this side of the reaction is +7. On the product side, I only have the +2 charge here. So in order to get those to match charges, I need to add in 5 electrons to the reactant side. So they're both +2. So let's go ahead and clean that up. I'm going to kind of squeeze it in, add those 5 electrons onto my reactant side. Next step, and we're almost done, you need to make sure the electrons match. So because we have 5 electrons in our reduction half reaction, it's reduction because it's going to gain the electrons, I need to multiply this whole reaction by 5. So 5 iron ions yields 5 iron 3 plus ions and 5 electrons. So now my electrons match, which is what we need. Last step, you are going to combine the two half reactions. You are going to do all of the reactants on one side, so 8 hydrogens plus the MnO4 negative ions plus the 5 electrons plus the 5 Fe2 plus ions from the other half reaction. And then let's combine all of the products. So we have the Mn2 plus ions, the 4 waters, and the 5 Fe3 plus ions. Oh, and the 5 electrons on this side as well. Now you would then at this stage, if anything is the same on both sides, you need to eliminate that from your final answer. So you should always be eliminating electrons because that is the point. You always want to make them match so that they eliminate. And then if there's anything else that's the same, you would cross it out. But it looks like everything else here is good. So this is our overall reaction. The 8 hydrogen ions plus the permanganate ion plus 5 iron 2+ ions yields manganese 2+ ion plus 4 water molecules plus 5 iron 3+ ions. So if they give you an example where you have to, instead of having hydrogen ions, it says it's in a basic solution. So remember, bases different from acids. There's just one extra step. You're going to do the same exact steps from before, but do one thing at the very end. And that extra step would be to add hydroxide ions to both sides to eliminate any hydrogen ions. And we'll take a look at an example so that we can see what that looks like. So here's our balanced reaction from that previous example. So this one's all balanced, but now let's say we want to do it in basic solution instead. So I'm going to, because we have 8 hydrogen ions, I need to add 8 hydroxide ions to both sides. The hydrogen ions and the hydroxide ions will combine to form water. So I have 8 water molecules plus the MnO4 negative plus the 5 Fe2+ ions yields Mn2+ plus 4 H2O plus 5 Fe3+ plus 8 hydroxide ions. Now you should see that we have some water molecules that are the same on both sides. There are 4 water molecules here, but 8 on the reactant side, so 4 of those cancel out. We don't have any more waters on the product side, and this is reduced to 4 water molecules on the reactant side. So this makes it in basic solution instead of the acidic solution from before. And that is how you balance redox reactions.